You may ask this question or not. What would we see at the speed of light? Well, for answering this question, we'll take a trip to space, so fasten your seatbelts and let's start our trip. One other thing before we do that, you should know, according to the theory of relativity, it is impossible for an object with mass to reach the speed of light. However, we can explore the hypothetical scenario of what we might see if we were traveling very close to the speed of light. Now, no further ado, and let's start. This is our spaceship moving away from Earth. Here is the main question: what would we see when accelerate? And next one is what optical effects would occur? And the answer of these questions will lead us to explore many fascinating phenomena of the universe. Our spaceship is begin to accelerate and the speed became unbearable, but it doesn't affect on our bodies. However, we can feel its acceleration, the thrust of the reactors which presses us against seats. One more thing is, at the light speed, the spaceship is equipped with a force field that repels dangerous object. Counting our trip, a first optical effect appears is the stars in front of us, which we get closer to seem to gradually move away. The universe contracts before us. The stars as light comes from a certain direction, but as we accelerate, the light rays appeared to come from the front.
So direction seems different when we are in motion. It is aberration of light or relativistic aberration. If an object is moving at very high speeds, the angle of incoming light would appear to be compressed in the direction of motion. As light focuses in front of us, its intensity increases. As a result, behind us will be dark and seems to widen. Relativistic of aberration brings another phenomenon. Imagining we are traveling through an immense grid representing the fabric of space. At the first, we will see a straight grid, but by speeding up, the aberration phenomenon distorts the image of the dark sky surround us. As the days go by, the grid seems to contract forward, and the straight lines bend. If we were past an object, it would appear to be slightly angled in our direction. This is called terrible Penrose rotation. Through our movement, objects seem contracted, and perspective is strongly distorted. As we move away from initial point in Earth, the planet's light takes time longer and longer to reach the spaceship, and if we zoom in using a telescope, we would see motion. It is the Doppler effect. Each second on Earth takes longer to reach us, but we receive it in slow motion. Also, their intensity seems to weaken as the image of the planet, while it is completely opposite effect in front. Here, the Doppler effect would come into play, causing the wavelength of light to shift towards the blue end of the spectrum, leading to a phenomenon called blue shift. This means that the light we see from stars and galaxies would be shifted towards the blue end of the spectrum, making them blue and brighter than they actually are, and clocks seem to take faster.
With precise enough equipment, we could measure the aberration and Doppler effects since the start of our acceleration in space. After long time in space, the reactors push us ever faster. At such point, some phenomenon will no longer be more optical illusions. Real physical effects will kick in, with irreversible consequences. Special relativity. A first consequences of relativity is time dilation. The universe is a huge four-dimensional fabric called space-time, made up of 3 dimensions of space and the 4th dimension of time. Inside space-time, all bodies trace a trajectory, since they all advance towards their future. You remember before takeoff, our spaceship was moving in the same way, but by picking up speed and zooming away from Earth faster, our trajectory gradually deviated from that of the planet. The axis of time is no longer aligned with the axis of people on Earth. And after coming back, we would have aged less than Earthlings because our trajectories in space-time were different. A second consequences of special relativity is length contraction. Objects in the direction of travel would appear to be compressed and distorted due to the Lorentz-Fitzgerald contraction, a phenomenon where objects are shortened in the direction of motion. From the starship's perspective, the entire universe is moving backwards for us, is contracted. Length contraction is a real phenomenon, but visually it would be almost impossible to see. And that is why imagine that we cross the orbit of a planet as it moves very quickly towards us. The planet length is contracted. But remember, the farther we look into space, the farther we look into past. And from our perspective, the back of the planet is located further in space than the front of it. The image that we receive from the back of the planet does not look like it because we receive the image of its back with a delay. Rather than contracted, it appears to be rotated. This is a phenomenon we have seen Tyrrell Penrose rotation. When we move very fast and look to our side, the edges of the object around us seem shorter in the direction of motion. This can be interpreted either as length contraction or as a rotation as a change in perspective. It is the same when people watching us would not really see our ship contracted, but rather rotated on itself. By accelerating more and more, we would perhaps expect to reach the speed of light at some point. But the truth is no, because the speed of light is absolute. You may try to catch a light ray, but from your point of view, it will always escape at the same speed, the speed of light. It is strictly impossible to exceed or even reach the speed of light. At best, our ship will continue to accelerate forever, and our field of vision will continue to shrink ever more until forming an infinitely bright spot in front of us, surrounded by a completely black sky almost at light speed. All optical effects would become extreme. Indeed, the theory of general relativity teaches us that the fabric of space-time is dynamic. It can bend in multiple ways. We could thus imagine creating a bubble around our spaceship, which we would propel faster than light. This called warp drive in reference to science fiction. It would no longer be a matter of zooming a vehicle through space, but of propelling the fabric of space itself. Our ship would remain motionless, surfing in a wave of faster-than-light space-time. Such a structure may seem absurd, and indeed it is currently thought to be impossible to achieve. Producing a warp drive would require bending space-time with huge amounts of negative mass from matter that doesn't seem to exist in our universe. That said, mathematics still allow us to calculate what we would see in such a situation. If we looked from outside, the warp drive would seem to appear out of nowhere. The curvature of space-time deviates the trajectory of light rays, forming a moving lens, which splits into two, one part moving forwards and the other retreating in the opposite direction. Light travels slower than the warp drive itself when it approaches. Light has not yet the time to reach us, and after it crosses us, we receive both the light which had not yet reached us and the rays which were emitted later. Looking from inside of the warp drive, we would see the sky contracted in front of us and very bright behind us. The universe would look extremely dark, and a whole patch of the sky would simply vanish from our view. The light emitted from there is too slow to catch up with us. A cone of the universe remains permanently invisible.